Hey guys, this is the lecture video over section 5.3, which is log functions and graphs of log functions. So we are going to be discussing a different type of function from the exponentials, but log functions are just the inverse of an exponential function. And exponential functions are what we talked about in the last section, and we also discussed inverses in the last unit. So these two things kind of go hand in hand here. When you are looking at a log equation or function, or expression in this case, it is read log base A of x. And the base of the logarithm is always a little subscript, and the number next to it is going to be like a normal size, size-wise, not a little teeny number. What this really means is the power that you raise this little base to that will give you the value of x. So you can translate log functions into exponentials and vice versa. And sometimes it's better to have them as logs, and sometimes it's better to have them as exponentials. But we're going to do conversions in both ways so that you can see them. So if you are trying to evaluate a basic log equation, you're going to be basically asking yourself, what power am I raising this little base to that will give me this other number? You're trying to find the power that works. So what I normally do is take each one of these log equations and set it equal to x, and then rewrite it as an exponential function. And then you're going to solve it using one of the exponential rules that we used before. So in this first one, if I just say, okay, log base 3 of 9 equals x. If I translate this into an exponential, the 3 becomes the base of the exponential. The x is going to come over as the power, and then the 9 is going to go on the other side. What power do I raise 3 to get 9? Now this one is pretty basic and straightforward. You can probably just look at it and say, okay, I raised 3 to the second power to get 9. But they aren't always going to be as straightforward. So in certain situations, you might have to actually do the rewriting of the larger number as a smaller number to a power, like we did in the last unit or section. For example, again, if I set this equal to x, it looks like 2 to what power equals 1/4. Now, when I have a piece of my equation here that's a fraction, I don't normally like to leave it as a fraction. What I typically do is take this thing and write it as 4 to the negative 1 power, just so that everything is an integer in it instead of having any fractions to deal with. 2 to the x equals 4 to the negative 1 is more in line with things that we looked at in the last section. So I can rewrite 4 using a base of 2. 2 to the x equals 2 squared to the negative 1 power. Now the bases match like they did in the last section, and when the bases match, you can throw them out. So this says 2 to the x equals 2 to the negative 2. And now these 2's go, and I'm left with x equals negative 2. And this might have been very obvious to you from the beginning, or maybe it wasn't. But we have the methodology to solve something like this because we did it in the last section. In a similar fashion for this last one here, I'm going to set it equal to x and rewrite 8 to the x power equals 2. And now once again, I need to take this larger base and make it a 2 to a power. So we have 8 is the same thing as 2 cubed to the x power equals 2 to the first. And I'm only putting a first power there as a placeholder because you're supposed to have a power there. That way when you drop your 2's, there's something there. And if I simplify this, it's 2 to the 3x equals 2 to the first. Now I can throw these 2's out, and I have the equation 3x equals 1. This is a very basic one-step equation. The only thing that I have to do is divide both sides by 3, and I get x equals 1/3. So you're looking for the power that completes your equation. And this is one of the ways that we're going to do some translations and then solve some equations. So that's going to bring me to conversions, which I actually just got done doing. When I am converting logs into exponentials and vice versa, I'm really just going to be doing some rearranging. So in an exponential equation, the base of the exponential becomes the base of the log, the little tiny number next to it. And then the other two pieces of the equation are going to switch locations. The x is going to detach itself from the a and go over to the side by itself, while the y is going to come over and attach itself. I said x and wrote y. The x is going to detach itself and go over to the side by itself, and the y is going to come over and attach to the a. A, y, then x. So log base a of y equals x. When you're going the other way, which is basically what we just did for those equations, you are going to be taking the log and eliminating it altogether, making the subscript the base of the exponential, and then again switching the locations of the two. The x was attached to the a, so it's going to detach and go by itself. The y was by itself, so it's going to come over and attach to the a. So a to the y equals x. Now, going along with this log stuff, we also want to talk about natural logs, because natural logs are their own thing. Anytime you're dealing with a natural log, it's understood that it's going to be a log base e, which is special. Regular logs deal with all the integers and fractions and things like that. Natural logs deal with e only. So when you're doing conversions, in the exponential equation, you've got y equals e to the x power, and we saw that graphed in the last section. To write it as a log, you're going to eliminate the e and replace it with an ln. And then just like with the log stuff, you're going to switch the location of the x and y. So the y is going to attach itself to the natural log, and the x is going to detach itself and go over by itself on the side by itself. So these are the 4 types of conversions that we might have to do. And in this next little part, we've got a few conversions that we're going to make. So we're just converting, not solving or doing anything else. We're just converting. So if you're converting number stuff to log stuff, you want to start with the word log. Now the base of the exponential, the 5 here, becomes the little subscript next to the log. And the other 2 values are going to change locations. So the -3 detaches and goes over to the other side. The 1 over 125 attaches itself to the 5. If you're dealing with something that has an e in it, you should automatically know that you're going to start with ln and not log. And then once again, these 2 pieces change sides. So the -t is going to go over by itself, and the 4,000 is going to come over and attach. In the next set, I'm going to add another one in here. Let's say we had ln of k equals 0.219. I don't know, just to put something in there. So the first one has a log in it. We're going to eliminate the word log and make this little dude here, the 4, the base of the exponential. The other two pieces switch sides. So the t will attach as the power. The 7 will go on the side by itself. Over here we have a natural log instead of a log. So we're going to replace the ln with an e. The k detaches over by itself, and the 0.219 becomes the power. And there's your exponentials. So the conversions aren't too bad, and actually we just got done doing some conversions with this thing here with 3 so that we could solve. So we're going to see a little bit of that again here in a moment. Before we do that, I want to talk about evaluating using a calculator, because this is a piece of cake. There are 2 buttons on the calculator that deal with logs. The problem with them is that they are very specific. The log button is for the common log only, which is logs that have a base of 10. So if it has any other base next to it, 2, 5, 27, whatever the case is, you can't use just the log button by itself. It doesn't work that way. It would be nice if it did, but it doesn't. Natural log, ln button, is the log base e, which I already mentioned. And again, it's very specific. You can only use the natural log button if you are dealing with e stuff. So when you're doing these types of problems where you're using the calculator, it's going to say just plain old log 15, plain old log 0.13, plain old log -4. Same thing with natural log. Whoops, too far. With natural log, it will say ln 7, ln 0.419. I don't know. And then you're going to use the buttons in the calculator to evaluate. So where it says log, you're going to push the log button. And the first one I put on here was log 15. Log 15 equals. And it'll tell you in the problem how many places to round to. I normally go to 4 decimal places just for good form. Go wherever it says to. If I go to 4, in this case, it's 1.1761 because I have to round up. Log, I put the wrong thing in. Log 0.13 gives me a negative 0.8861. Again, I have to round up. And then if you put in log of a negative, you get this error message. The calculator is not going to evaluate log or natural log of a negative number or 0. We cannot evaluate these values. They are not within the domain of logs. So you will get an error message every time. So these don't exist. That looks bad. Doesn't exist. All of them don't exist. This one in particular doesn't. Because you get an error, it's not going to work. For natural log, we use ln instead. Same rule applies for negatives and 0. You still can't do it there. ln 7 is 1 point, I'm rounding 1.9459. And ln of 0.419 is negative 0.8699. So those are a piece of cake because you're pushing buttons on the calculator. Now we're going to get into some graphing. Okay, so for graphing, if we're graphing by hand, we're going to be using a table. And typically it is best to use the exponential form to look at these, especially when you have log bases that are something other than a common log or a natural log, because it's hard to find a graph, like a parent graph to go by, that uses one of the other bases. So typically it's best to translate into an exponential equation and then make a table of values, where in this case we're going to pick for y instead of x. And that's just because when we do the conversion, for example, in this one, if I convert it, it becomes 2 to the y power equals x. And now the y is the independent variable and the x is the dependent variable. So when we select our values for our table, we're going to select values for y and solve for the x. So I'm just going to pick a few values here. -1, 0, 1, and 2 maybe. And plug in to get a good nice picture of this graph. So I start with -1, 2 to the -1 power, and you can put that into the calculator and it will give you a decimal, which is fine. You're going to have to estimate where any of these decimals are. But 2 to the -1 power is 0.5. 2 to the 0 power is 1. 2 to the first power is 2. And 2 squared is 4. So all I did was plug each one of these values in as the power, and that's going to give me my x coordinates, because again we had to switch these. So 0.5 is at -1, which is right here, and 1 is at 0, 2 is at 1, and what's the next one? 4, 2, 3, 4 is at 2. So these are going to resemble exponential curves, like this. And if you look at what this graph is doing, it's got an arrow on the left and an arrow on the right, which indicates a domain of all real numbers. Also, it's got an arrow at the bottom and an arrow at the top, which indicates a range of all real numbers. You have to pull up another sheet. Ugh. Ouch. Oh, you know what? And I just told you a lie about the domain and range, because this thing is going down. Let me get my eraser, but hold on, I'm trying to pull something up. I gotta fix this right here, because I didn't draw this very well. Okay. We just got done talking about this. So where's my green? I'm trying to do this too fast because I have to go to class. So my apologies. When I do this thing, it comes like this, and it's getting real close to 0. It doesn't keep going. The domain of log functions we just talked about, you cannot put negatives into a log or 0. So if you do that, you get an error message, which I just got done telling you, and then I can't believe that I said this. But the domain is round parentheses 0, because you're not allowed to touch it, to infinity. You can't put in there negatives because you won't get a real number. Sorry. I know that you probably were like, what? What'd she say that? Because we just talked about it. What I'm trying to pull up here is the sheet that goes along with
the transformations. So I want to find that Word doc. I think it's right here. Okay. So I'm going to include these translation guides here for the exponential and log functions because they have all of the different looking translations for each type of log. So in this particular sheet, it uses log base 2 as your base function. And then it kind of adds things into the function to show you what happens for each one. So when I do these translations, I'm going to do them using the transformation sheet. And then that way you can kind of follow along with the different translations and move this thing accordingly. So they're very similar to the translations that we did in section 3.5, which was the whole section about translations. It's just where they are in relation to the logarithm that's going to kind of tell you. So you still have the shifts where you're adding or subtracting a number on the outside or the inside of the parentheses. You have reflections where there's a negative on the outside or the inside again. And then you have stretches and shrinks based on numbers being multiplied outside or inside. So we're going to start with the next example having a log base 1/3, I think, which I did the base graph of already so that you could see it. And we'll do the translations based on this picture. So I changed this thing to, first of all, y equals log base 1/3 of x as the base. I took out the 5 and the negative, 1/3 is the base, and I just made it a standard log equation. And then rewrote it as an exponential so that I could do the graph like we did in the last example. So I plugged in some points for y and got some points for x so that we could start here and then work our way through the translations. Now, in this particular example, there are two different transformations. There's a number being added on the inside, and there's a negative being brought in on the inside. So we're going to start with the number being added on the inside because this number being added on the inside is the horizontal shift. And it says that on this sheet, which again you will have included, horizontal shift, number being added on the inside. Now remember, with the horizontal shift, the graph moves right or left, and it does kind of like the opposite of what you would think. Oh God, I wish I could draw straight lines, but I can't. Here we go. Horizontal shift. And in a horizontal shift, we do the opposite sign. So we're going to -5, and we do it to the x's. So I'm going to take the x's and subtract 5 for my new ordered pairs. So I'm going to begin with +3 minus 5, which is -2, -1. 1 minus 5, which is -4, -4, 0. And then I'm going to do 1/3 minus 5, which is going to give me a decimal, and I'm going to use the decimal. It's -4.6, repeating, comma 1. And then 1/9 minus 5, and again, I'm just going to use the decimal, which is -4.8, repeating, comma 2. So this would move this thing to the left 5 units. And then we're going to take it and do the next one as well because it only wants the, well, it wants a description. I guess we shift it left 5. And then we're going to reflect it. There's a negative on the inside. So again, I'm going to go back to my sheet so I can point this out. We've got a negative on the inside of the parenthesis, which is a horizontal reflection. And horizontal reflections reflect over the y-axis.
And if you remember when we did this back in section 3.5, to create this reflection, you change the sign on all of the x coordinates only. So I'm just going to go back to my chart and take all these x's and change the sign on them for this horizontal reflection. And I'll make myself a little note here that I am change sign on x, which is going to make this -2 a +2, and -4 becomes a 4, and -4.6 repeating becomes 4.6 repeating, and -4.8 repeating becomes +4.8 repeating. And so if this graph of my base function, which they didn't say to do that, but I just put it on here so we could look at it. Now I'm going to plot my new points that are going to give me my new picture. And they look like 2, -1, which is here, and 4, 0, and 4.6, which is like right here maybe, 1, and then it looks like 4.8, 2. And so this thing is curving real close to +5, and then curving back around down like this. Okay. So there you go. And now let's see here. It looks like the domain is from -infinity, and then it's getting real close to 5, but it's not going to hit 5. -infinity to 5. Close, but not touching, so round parenthesis. And then the range is going from the bottom here to the top, so it looks like all real numbers. So we're going to use this transformation sheet. I'm going to come back over here. Here it is. We're going to use this transformation sheet to be able to create our transformation graph. And we're going to say what we're doing to it, which I think is just going to take the parent graph and flop it all around. So just make sure that you're going to change your base in there so that you know what base is happening. And then if it asks about the vertical asymptote, that's going to be that vertical line that it's getting really close to, but not crossing. So when you do these, I think the computer is going to do them for you, and then you'll have a better looking picture than the one that I can make here. So hopefully that's the case. But that's graphing log transformations. Now we're going to talk about some basic log and natural log equations, and then let me see if that's it. Yeah, okay. Wanted to make sure I had enough time, and I didn't want to stop. So in these basic exponential, or log rather, equations, we are going to be changing them to exponential equations and then solving. So for log equations, we're going to do our transformation, dropping the log, making this little guy here the base, and flip-flopping the other two. So this says 16 to the 3/4 power equals x. And in this case, because x is by itself, all we have to do is take this and put it in the calculator. 16, raise it using the caret button, and then you can use 3/4 in a parentheses, And it's going to just spit out the answer for you because 16 to the 3/4 is a nice number. It's 8. Something like this is a little tiny bit more involved, but that's okay. We're going to take 3 as the base, -2 as the power, and then all this stuff here as what you're setting it equal to. And this is pretty similar to stuff that we did in the beginning. Because we have a 9 that can be rewritten as 3 to a power. So we're going to rewrite 9 as 3 squared. It's already being raised to the 2x power, so we have to leave that there. And that's set equal to 3 to the -2. We can simplify this power by multiplying. So you multiply these two powers together and we get 3 to the 4x power. And now we have the same base, so we can throw them out. Drop it. -2 equals 4x. And divide both sides by 4. Now, -2 over 4 is not in simplest form, so we want to simplify. -2/4 becomes -1/2. So for the log ones, it's going to be similar to what we saw in the beginning. With natural log, we are going to have to rewrite using e, because ln gets dropped and we rewrite it with an e. This guy over here becomes the power, and we set it equal to whatever was next to the ln. Now, e raised to a power is just some number, and you can put it into the calculator to find out what that number is. If I put e to the 3rd power in there, I type second ln to get my e, and I put in a 3 for the power, and I hit equals. It's going to give me this big long thing, 20.085, and it keeps going. And I can leave that number in the calculator and subtract 1 from both sides, rounding at the very end. So I have that big long 20 in there, hit -1 equals, and now it gives me another big giant long answer, and I can round it wherever I want. Again, just to be safe, I'm going to go to 4 decimal places, 19.0855. And if they ask you to round to a different place, then that's fine, just round there. All right, this one looks a little bit weird. We're going to replace this natural log with an e, but the power is 0, equals ln of x squared. Now, if you put in the calculator e to the 0 power, you get the same thing you get when you raise anything else to the 0 power. E to the 0 power is 1. And now we have another equation, 1 equals ln of x squared, which we can rewrite again using e if I drop this ln and make it e to the 1st power equals x squared. And again, I'm going to let the calculator do the work for me. E to the 1st power gives me that big long 2.7 whatever, and it keeps going. Leave that in the calculator and take the square root of both sides. That way, you hit second square root, second ANS, and it's going to put that big giant long number in there, and you can take the square root of it, giving you 1.6487 for your x. So let the calculator do most of the work for you and round at the end so that you make sure that you get the right decimals, because if you're off by a decimal or two, it's going to mark it wrong, even if it's right. So that is the intro to the log stuff. You're going to see some more log stuff in section 5.4 and 5.5. Properties and solving equations. 5.5 also gets back into exponential equations as well. So you'll be able to solve both types. And then that's the last section. And the chapter 5 stuff that you're seeing now will pop up on the final exam, but there is no test over this chapter 5. As always, if you have any questions, please feel free to email me or Becky Pearson, or see any of the tutors that will be available. After Thanksgiving break, I will be out on leave, so please make sure that you contact Ms. Pearson if you have any questions about any of this stuff or videos or anything like that. But good luck.